Hello everyone, my name is Himani Sharma. Today I am going to present the work titled Stability Analysis and Dynamical Behavior of Optimal Mean-Based Iterative Methods. These are the outline of my presentation. Now, finding the solution of nonlinear equation of the form f of x equal to 0 is a very important task in the field of numerical analysis. The most used technique in this regard is the approximation of solution by iterative methods. Newton's method is one of the primary methods which converges linearly for multiple roots and quadratically for simple roots given by question number 2. Now, there are many one-point iterative methods with higher order as compared to Newton, such as Halley's method, Super-Halley's, Chebyshev method, etc. But they all have their practical limitations due to second-order derivative involved. On the other hand, multi-point methods are in a vast number that use Newton's method as the first step, and also they are free from the computation of the second order or higher order derivatives. Many of such methods we can find in the literature in the last decades. Now, in the recent times, the stability analysis or the dynamical behavior of the method has been a very important subject to study. In this study, a rational operator is constructed, and by the use of affine transformation, the iterative family is conjugated to that rational operator, so that we can check how the family behaves dynamically. The works of Kelly and Schroeder were the starting of this subject, where they used the Newton method on quadratic polynomials. Also, in recent years, it has been widely used on iterative method without memory. Now, the iterative family which we are considering in our work is given by equation number 3. This family is optimal and has error equation given by equation number 4. Firstly, we will recall some basic concepts of complex dynamics. So, if R is a rational function defined from a Riemann square to C to C, then orbit of a point Z naught belong to C will be defined as the successive images of Z naught applied on R. Also, we are interested in the study of asymptotic behavior of the orbits depending on this initial point Z naught. So, to obtain these phase spaces, we will classify the initial points from their asymptotic behavior. Further, Z naught belongs to C will be a fixed point if R Z naught equal to Z naught. It will be a periodic point of period t greater than 1 if R power p Z naught is equal to Z naught and R power k Z naught is not equal to Z naught for k less than p. It is called a critical point if at Z naught the derivative of the rational function is 0. And further, the fixed point is called attractor if R dash Z naught mod will be less than 1. If it is equal to 1, then it will be parabolic. If it is greater than 1, then the fixed point will be repulsor, and super attractor in case of 0. The basin of attraction of an attractor alpha is defined to be the set of free images of any order such that it such that n approaches to infinity. Now, to present the complex analysis of the concerned family, we construct a rational operator on a quadratic nonlinear polynomial, and we will then find the fixed points and critical points of that operator. Next, we will generate the parameter planes and dynamical planes. So first of all, the scaling theorem that let fx be an analytic function on the Riemann square. If V is composition of f or neta, where neta is ax plus b to be a linear map, then the fixed point operator obtained from the iterative family will be conjugated to another operator, and by studying this operator we can check the dynamics of our concerned family. Now, where we will take a quadratic polynomial px x minus a into x minus b, having roots a and b belonging to real numbers. And now, if we apply the iterative family on this polynomial ph, we obtain a rational function h, which depends on the root a, b, and the parameter alpha. Now, if we use a Mobius transformation hx equal to x minus a upon x minus b with the following properties, then that operator H alpha can be conjugated to operator G alpha, which will depend on the parameter alpha only. Now, if we further, we will be finding the fixed points of this operator. So we have to solve G alpha x minus x. So if we solve this equation, we will be getting fixed points. Now, since this equation is in alpha, so we will give different values to alpha and then compute our fixed point. So for different values of alpha, we will be obtaining different number of fixed points. The description of which it has been given here. Now, next will be the stability prospect. For stability of fixed point, we will be finding the derivative of the operator G alpha, and then we will put one by one the fixed point in that derivative. According to that value, we will be classifying these fixed points according to repulsor, attractor, or parabol. Then we have to find the critical points of these operators. For that, we will have to solve G alpha dash x equal to 0. So since this expression will also be in alpha, so we will be giving different values to alpha, and we will be getting different number of critical points for different cases as described here. This table describes different critical points according to different values of alpha. Next, the dynamical behavior of operator depends on the values of parameter alpha as we are studying. So a parameter plane we will be drawing, which is defined as a mesh in the complex plane, where each point of this mesh corresponds to a different value of alpha. Its graphical representation shows the convergence analysis of any method of the concerned family which we are taking. So what we do, we use a free critical point Ci as initial value, and then we, if a method converts to any of the roots starting from this initial point, then that pixel is colored red, otherwise it is colored black. So we can see in this figure, the black points means that for those values of alpha, the method will not converge. Further, we can also illustrate the behavior of the fixed point through the dynamical planes. Generating a dynamical plane allows us to see the stability of a method for specific values of alpha. So this is defined as a mesh in the complex plane where each point of this mesh corresponds to different value of the initial estimate x naught. Its graphical representation shows the convergence of the method to any of the roots now starting from the initial point x naught. So to study the stability, we can use the dynamical planes, and we can take the values of alpha from here, from the parameter plane. The values inside the black areas, for that values of alpha, the method will not be converging, and the method will not be considered stable. And for the values of alpha in outside the black region, the method will show stable behavior. So these are some dynamical planes for different values of alpha. We can see the third plane in which we can see that for this particular value of alpha, we have black areas. So this method will not be considered stable. So conclude, in this work, we have explored the complex behavior of the iterative family and by complex dynamical rules. So we have taken the theory of Mobius conjugate transformation, in which we conjugate our iterative family through a rational operator, and then we analyze that rational operator by finding fixed points, critical points, and then drawing the parametric plane and dynamical plane. This study helps in identifying the stable or unstable family members, which in turn can be employed to several practical problems. These are the references. Thank you.